you guys need to consult technology. I'm not going to teach you row reduction in here. All right, so like I don't expect you to. This problem will probably be like out of bounds for a test, right? Unless I give you some help. See, because you have to see past the fact that there are three equations that aren't really distinct. Really, you can just keep these two, which means that's the generic solution. And there's some linear algebra here, I think, that I'm glossing over. Yeah. All right. What's this one? Here's one real, one complex. That can happen. Here I have eigenvalue 1 or eigenvalue plus or minus I. So the eigenvalue 1 gives you an eigenvector 1, 1, 1. The eigenvalue I gives you a complex eigenvector, like if I put u equal to 1, 1i minus 1. So I get this complex solution, which you peel off these two real solutions from, and you get the one real solution. So there's sort of a mixed case. One real eigenvector, one real eigensolution, and then the real and imaginary part of the complex eigensolution going together to make the whole thing. You guys, I mean, I hope you see you can use what I have spent the last two classes to do a lot of different cases, right? I mean, yeah, sure, we're missing something, but we also cover a lot with what we've already done. And that brings us to the matrix exponential. So what is the matrix exponential? Well, the matrix exponential is what we do. It's how we solve what else is out there. All right. So I'll put this away and I'll write on the board because I don't want to. I mean, I need the projector to show you examples because, good grief, how long would it have taken me to work through even 3 of those examples? You know, we'd be here till Christmas doing that. And I don't think you need to write those down. You need to read them and try to understand them, like do some scribbling on the notes on top of it or whatever until you own them for yourself. Is it going to let me put away the... Are you gonna let me put up the thing? Stop presenting. Yes, I am sure. Thank you. All right. So now we're not going to finish the discussion of the matrix exponential today, but we'll get a good start on it. But that's the thing I haven't shared with you yet. The rest of the story is the matrix exponential. The matrix exponential, actually, truth of the story is I could just teach you the matrix exponential alone and that would do everything. But you don't really want to do that because it would be sort of like, you know, oh, there's a rat in my garage. Let me go find the sledgehammer. I mean, it's not a good way to kill a rat, you know? Just saying. I think the right way to kill a rat is with a cat. Maybe a dog. Let's see here.
Wouldn't there be satisfaction in killing it with a sledgehammer?
Rats are surprisingly fast. They're kind of scary to try to kill. I have tried to kill one before using brute force, and I tell you, it's, I don't know, they're faster than you'd think. Pellet gun. I did find my well, I should probably stop talking about it. Who knows what's legal here anymore. Let's see here. So the matrix exponential. So here's what it is. The definition of the matrix exponential is if we have e, I'll use a b. E to the b is equal to I plus b plus 1/2 b squared plus 1 over 3 factorial b to the third power, and so forth and so on. In terms of series, this is the sum n equals 0 to infinity of b to the power n divided by n factorial. It can be shown by careful analysis. First of all, you can define a notion of how big a matrix is. You can define the length of a matrix, so to speak, by the length of the corresponding vector. So like if you take the matrix, for example, 2 by 2 matrix 1, 2, 3, 4, you just say it's the same as the length of the vector 1, 2, 3, 4. You just take the matrix and you list out its entries, and that's the corresponding vector. And so you can judge the quote-unquote length of a matrix by just the length of the corresponding vector. With respect to that notion of length, you can define convergence of series of matrices and sequences of matrices and so forth, just like in calculus 2. And with respect to that notion of convergence, you can prove that this series is in fact existing for any matrix, right? I'm not going to do that in here because that's analysis and it doesn't belong in this course, but rest assured that this is well defined for any matrix. So that's pretty awesome. So that means we can calculate this thing for whatever you like. There's also some really, really cool properties here. Let's see here. If I have, let's see here. Let's see what would be the next thing. I guess the next sort of very low-hanging fruit you might notice is that e to the what? E to the 0 is what? It's just I, right? And let's see here, what else can we prove? If AB is equal to BA, all right, then you can show that e to the A times e to the B is equal to e to the A plus B, all right? Let's see how that works out, okay? So like, I'll do it up to a couple orders. I won't go too far. But actually, I mean, I could give you the full calculation, but let me behave and not do that. So this is I plus A plus 1/2 A squared, and I'll just do it to quadratic order. How about that? Right? And so if you multiply this, what do you got? You got yourself I plus A plus B. That's the linear terms, right? And the quadratic terms are a little bit more fun. So plus 1/2 A squared plus A times B plus B times A plus 1/2 B squared plus da da da. And all right, so if A and B commute, right, I can rewrite this as I plus A plus B parentheses plus 1/2 A plus B squared plus da 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 da. Because this up here, right, can be written as 1/2 of A squared plus 2AB plus B squared, using the fact that AB is equal to BA, right? And then I can factor A plus B times A plus B, so I get A plus B quantity squared. And then, of course, you see what this is. Well, that's just e to the A plus B. To make this argument careful, of course, you could use the binomial theorem and the Cauchy product, but okay. What's actually more interesting is to think about what if A and B don't commute? What if AB is not equal to BA? What would be here? What is it? Are you talking about this? That's fine. You can ask.
I was just curious about the AB in the middle, because if we take the 1/2 out, doesn't it have void in the middle? So I'm just confused.
Yeah, I think you're right. What have I done? Huh. I guess I better write it down. So these terms, I can't see past what you're saying at the moment. 1/2 a squared plus, like you said, 2ab plus 1/2 b squared.
Don't you only have one AB term?
Oh, yes. Oh my goodness. Thank you. Yes. Idiot. Me, not you guys. Thank you. Duh. The point is that this, goodness gracious, this is 1/2 of a squared plus 2ab plus b squared. And the place you use the commuting is to get that a plus b times a plus b, all right? Which generically speaking would be what? This would be a squared plus ab plus ba plus b squared. That's the thing. When matrices don't commute, so when you square a plus b, you don't necessarily get a squared plus 2ab plus b squared. You get a squared plus ab plus ba plus b squared, is the point. But if they commute, then in fact this factor, this is just 1/2 a plus b quantity squared. Thank you. Thank you, thank you, thank you. Well, that explains. Let's see here. I think if you look at it, you could see that you have, let's see here, plus 1/2 the commutator of a and b. Plus dot, 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 dot. What's the commutator of a and b? Commutator of a and b is ab minus ba. So, it's not obvious from this. Never mind. Let me. I was hoping to see something else while we're in the middle of this, but I'll behave. I'll behave. Okay, so we fixed that. Good, good, good. And what I was mentioning, you guys, is that if you don't have commuting, there's something like this that happens. And because I don't remember, but it's 112. So like in the case that A and B don't commute, there's formulas that are known, but they're rather complicated. This thing I'm writing down is the so-called Baker-Campbell Hausdorff formula. Or the BCH identity. Don't worry, you don't really need that for this course. My point is that when A and B don't commute, the departure from the laws of exponents is known, but it's also rather complicated. Knowledge of these commutators and nested commutators is enough information to figure out how to multiply e to the a times e to the b. All right, my point in all this was very simple. Let me get to the point before I waste our 5 minutes here. Oh, I'm sorry. Really low-hanging fruit, just to get to it. You notice that then e to the a times e to the minus a. Notice that a times minus a is equal to minus a times a. That's true for matrices. Any matrix times minus itself. Any matrix commutes with minus itself, okay? So take b equals minus a. So if I have e to the a times e to the minus a, I get e to the a minus a, also known as e to the 0. So there's I, and so hence e to the a inverse, the inverse of that matrix is e to the minus a. So the problem of finding the inverse to the matrix exponential is really simple. That also shows you that any matrix exponential is an invertible matrix, which is going to be important for us because that means that next class we're automatically getting a solution matrix from the matrix exponential. Anyway, more on that next time. Thanks, guys. Sorry for going over.